Hello. I'll start the presentation of Team 37, which consists of Seoul National University Hospital and Seoul National University. We participated in the Datathon under the theme of a study on the anesthetic management model, predicting the increase of anesthetic during surgery in real time. It's a table of contents. We will present in the order of introduction, methods, results, and discussion. Its introduction. During surgery, the patient does not feel pain, and if it cannot be detected and mediated, it causes great stress to the patient. Therefore, in order to mediate this, the medical staff judges that the patient feels pain by looking at the vital signal. It's an issue. So pain is different from pain. However, the patient cannot complain to the medical staff that he is sick during surgery. Therefore, the medical staff should judge the pain only by looking at the patient's vital signal. Let me tell you a good example to solve this problem. However, these are not measured during surgery and have discontinuous and subjective drawbacks. Therefore, our team would like to develop a model that predicts the increase in anesthetics that mediate pain using data such as electrocardiogram and artery blood pressure. Through the study, the goal is to create a model that helps medical staff make clinical decisions related to anesthetic administration. Data collection part. VitalDB was used, and the collected data and sampling rates are as follows. The data included through the collection and exclusion criteria were 1,110 cases, and 100 cases were selected. First, we define the intra-op. The start of the operation was defined as 5 minutes from the first increase in the anesthetic, and the end of the operation was defined as 5 minutes before the increase was 0. In addition, for the increase in anesthetics, the array was labeled as 1 minute ago, and all other than that, it was labeled as 0. This is a dataset configuration. The data pre-processing is as follows, and the data was partied 80-20. We made a total of 6 models. Largely, we developed the CNN and LSTM models. Each model is divided into if only is used and if only ECG is used, then both are used. 680 was the best performance on the CNN, and 675 was the best performance on the LSTM. We developed a deep learning model for predicting the increase of anesthetic during surgery before 1 minute using raw data of ARD, ECG. Input of ARD ECG reached the best performance for CNN model, while input of ARD reached the best performance for LSTM model. For both model, input of ECG reached the worst performance. These results are thought to be insufficient pre-processing of ECG. Since the model predict the need of increase in anesthetic before 1 minute, it is thought to be useful for practitioner to modulate the pain of a patient undergoing surgery. Throughout the work, we experienced the importance of pre-processing the vital data since there was various type of noises disturbing the model to learn necessary features. We divided the pre-processing into 2 steps: denizing the signal, and then assess the signal quality to exclude data with abnormal beat from input. The noises in the data include baseline wandering caused by the patient movement, noise induced by electric cautery in the surgery, and electromyographic EMG noise. Among these noises, we focused on the removal of baseline wandering by bandpass filter and Savitsky-Gale filter. Since smoothing by these filters can distort the original signal, we learned its importance to choose appropriate filter for given task. For the next step for pre-processing, it is also important to choose the clean data for training the model. Since ECG, ARD are periodic wave, we plan to detect the peaks, for example our peak, from ECG, and exclude, if the number of peaks are abnormal. And then W. And then we can evaluate the shape of the beat, and exclude, if it is irregular from other beats. Secondly, only 1,000 custades met the inclusion criteria, which is not enough for training the deep learning model. So gathering more data can increase the performance of the model. Input channels used for the model were ECG and ARD. The other vital data, such as photopulthesmograph Y and blood pressure, also contains the hemodynamic status, so including these vital data to input can increase the performance. Thank you for listening.